Hello, and welcome to Mr. Jackson's chemistry class. Today we're going to start our new unit, bonding. And we'd like to start off with talking about Lewis dot structures. Lewis dot structures basically just represent the valence electrons. Okay? And valence just means outermost shell. So if we look at a electron configuration of some elements, so let's look at beryllium, which has 4 electrons and 4 protons. We'll call it neutral. Beryllium basically goes 1s2, 2s2, and is done. Well, 2 is the highest shell that we see, and there's only 2 electrons, so beryllium has 2 valence electrons. And let's go with phosphorus. Okay, phosphorus is right here, it has 15 electrons, so let's assign them their electron configurations. So phosphorus, we have 1s2, 2s2, 2p6, 3s2. Let's go to the third row because phosphorus is on the third row. 1, 2, 3. But I also have to put some p electrons in there to get all 15. So 3p3. So we can see that the valence shell is the third energy level because that's the highest level it's using. And there are 5 electrons in that shell. So if you just simply count the S and P boxes to get to something, so beryllium 1, 2, and phosphorus 1, 2, 3, 4, 5, you actually can do this by just using a periodic table. Okay, so we have 2 in beryllium and 5 in phosphorus. So if you just simply count the S and P, and that even works for the ones on the fourth row, because remember this is the 3D. So if I was going to do, let's say I'm going to do gallium, okay, which has 31 electrons. Then to do all 31 electrons, I would simply just go gallium, 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then I go through the 3d area to get to gallium, which is in the 4p1 spot, 3d10, 4p1, and even though I've actually got a D in here, it does not count towards the valence shell because my highest number is 4. And so I would have 3 electrons in the 4th energy level. So gallium has 3 valence electrons. So we would go to gallium over here, and we go 1, 2, skipping the D's because they belong to the 3rd energy level, 3. Okay, so that is what we've been doing all along, is using this electron configuration, but now we're going to use it in a different way. So you can only put 8 dots around the symbol, and on each side of the element, okay, whoop, you can only put 2. Forgive me, that means 2 is what we want. 2 dots on each side of the element, okay, symbol. So let me erase that. It's a total of 8. We'll get to that in a minute. I apologize. So 2 dots around each side of the element symbol. Okay? So this is what we want to talk about. I want to show you beryllium's electron dot structure. So all I'm going to do is I simply just take and add 2 dots. Okay? But the most I can do is, if you think about it, is I can only do 2 on each side. The total I can put is 8, but I can put up to 8. Now there is a rule that you have to put 1 on opposite sides, and there's a certain mechanism like 1, 2, 3, 4. That's not that important because you really just want to be able to see how many valence electrons. So let's find 10 and let's count its S and P electrons. So 10 is right here, 50. And so counting the S and P, it's 1, 2, no, the D's all belong to that row, 3, 4. So it would need 4 dots. So I'm going to go with 1, 2, 3, 4. So that would be the Lewis structure for 10. So this is very, very simple. All you got to do is count the outermost shell electrons and then put a dot for each electron that you've counted. Okay, let's go do neon really quick. Neon is found on the 2nd energy level right here. And so I would count 1, 2, 3, 4, 5, 6, 7, 8, which is the most you'll ever see around any symbol. So 1, 2, 3, 4, 5, 6, 7, 8. And as you notice, I'm not putting more than 2 on each side of the element. And I was thinking earlier, remember, the most you'll ever see is 8, because once you reach 8 electrons, which is a noble gas except for helium, then you end up going to the next row. So the most you can ever get is 8 before the next row comes in. So 8 is the most you'll ever see around a noble gas configuration, or electron dot structure, okay? And a noble gas will have as most as 8. So nitrogen is right here. So it would have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And that's pretty easy to read. And if you ever really want to do a different, if you wanted to put 2 on a side like this, let's say you wanted to do 1, 2, 3, 4, 5. That's not incorrect, but just no more than 2 per side, because it still is easy to read and see that situation. So how many valence electrons would they like to have? They would love to have 8. Okay, 8 electrons. This is known as the octet rule, or rule of 8. Okay, and elements can get a stable octet by electrons by either trying to gain electrons or lose electrons. They would like to gain and lose. So this is going to lead me into the next idea I want to teach, okay? So they would all like to be like a noble gas, but they have to do it in different ways, okay? And the reason why we're studying these Lewis dot structures and these valence electrons is because they are the first electrons to interact whenever 2 elements come in contact. So if you think about it, if you have one element and it has outer electrons, then what happens is it comes into contact with another element, and it is these outer electrons that are first to touch, and so they do a lot of the chemical reacting. And so we need to know how many valence electrons each element has. That's a great thing to know, and it's very important, okay? So that's the reason why we draw Lewis dot structures, because they're a quick start to knowing how many outer electrons they have. And they're very easy to draw, okay? So you should be able to look and find any element on the periodic table and quickly draw their electron dot structure by identifying their outermost electrons, okay? So make sure you know that. Why do we need to know that? Well, this is because elements love to become ions. What are ions? Ions are charged atoms. And charged atoms that actually can be either a positively charged or negatively charged. Well, the big question is, how do they get those charges? They get those charges by simply gaining or losing electrons right here that we talked about. They gain or lose electrons, and they do it based on how close they are to the noble gas. Their desire is to have these 8 electrons, which is called the octet rule. So everything would like to be like helium, or neon, or argon, or krypton, but they don't ever become those elements. They just act like those elements, okay? So if I gave you $20 billion, you could act like Bill Gates, but you don't become Bill Gates, okay? So the truth is, a lot of elements do this when they run across other elements. So when you're eating food, when you're putting chemicals together, when you're cooking, whatever you're doing, whenever you put atoms together in any form or fashion, their outer electrons begin to interact. And if there's a benefit to swapping and changing electrons and becoming charged, they will do that. So knowing the outer electrons is super important. So let's move on. We talked about the octet rule above. It means 8 electrons in the valence shell. Okay? And that's very important to know. And what we want to talk about is, how can we predict? Let's look at a basic periodic table here. Okay, I've shrunk it down. And let's just look at the periodic table. We have the non-metal area and the metal area. Okay? And we're going to talk about the most common ions. Common ions fall into the S and P area. Okay? And they commonly behave the same. If you look at fluorine, fluorine has 7 outer electrons. If it could get one more, it would have 8 and feel like neon. So fluorine loves to take on electrons. But if it does that, fluorine takes on electrons because fluorine has the atomic number 9, okay? And so if it has 2 electrons in the first row, and if it has 7 on the next row, so 1, 2, 3, 4, 5, 6, 7, if it takes on another electron, it's going to have 9 protons because that's its atomic number, okay? And then it means it's going to take on an extra electron. It's going to have 10 electrons, so they'll be greater. And so what's going to happen is that fluorine is now going to have a -1 charge, okay? Because it has more electrons, which are negative, than the protons. So fluorine and all the other ones in its row would like to become -1, okay? And that's pretty simple. But look at sodium. Sodium, if it wants to become like argon, it's going to have to steal 7 electrons, and that's a lot of work. If it just took its 1 electron and gave it away to like fluorine, then it would, instead of behaving like number 11, it could behave like number 10, which is a noble gas. So sodium has 3 levels, and its outer level only has 1 electron. If it can get rid of that 1 electron to some other element, it then has full shells below, and these full shells could then become its now new valence shell. So it loves to donate, but then if sodium has 11 protons and it gives away an electron, and now it only has 10 electrons, which is acting like helium, neon, then what happens is now the protons are greater in number, so sodium, sorry I forgot that guys, I have to put Na, becomes positively charged, okay? So these in sodium's column love to be +1, okay? And so we can actually figure out most common states. These right here is too hard to gain, so they actually like to become +2. They love to give away 2 electrons and act like the noble gases. But now remember, the noble gases don't want to gain or lose. They're already happy. So they have no common charge, ion charge. They just want to stay neutral, okay? Well, let's look at this one, oxygen. Oxygen is only 2 away, or it could give away 6, but that's a lot of work and a lot of electrons to lose, so they're probably going to steal 2. So gaining electrons, it loves to be -2, okay? And so all the other ones in its row. Well, what do you think this one is? Look at the pattern. Yep, that's right, -3, okay? So phosphorus would love to gain 3 and act like argon, and that's what it does, okay? But let's look at some other ones. Now we're at a problem because 8, half of 8 is 4. So now we're at carbon. So carbon is actually in the middle. It could actually lose 4 or gain 4. So it actually can be either charged. It depends on who it's reacting with. But now that we've crossed the line, boron, okay, boron has to gain 1, 2, 3, 4, 5 electrons. That's a lot of work. But it could lose simply 1, 2, 3 electrons and then act like helium. And that's what it does. So boron's family loves to be +3. So these are the most common charges of the common ions in this periodic table. We're not going to study the F area because they're such rare materials. We are going to work with some of the transition metals, and I just want to let you guys know, but they are so much in the middle and they're so unique. They like so many different positive charges that we can't actually memorize one charge or another. They are very good at going in all kinds of directions and losing electrons, so and becoming positive. So we are not going to memorize any particular row here, like or column like we are here, okay? So we can memorize these S and P areas, but we will not memorize the D area, okay? Because there's just too many possible charges in here that they can have, but we will work with them, okay? And so let's do this really quick. How about calcium? Well, we got to find calcium in the periodic table right here. Calcium's in this row. So calcium, I'm believing is +2. And if there is a charge and it is an ion, we like to put ions charges in the upper right-hand corner. Okay, so let's guess at phosphorus. Phosphorus is right here. So what's your best guess? Well, let's look. That's right, 3 over -3. That would be its best possible condition or electron state, ion state, I should say, to help it out, okay? Boron is right here. So its most common ion state is +3. Fluorine is right here. Its most common state then would be -1. And the last one we're looking at today is krypton. Krypton is in the noble gas row. It does not want to gain or lose any electrons. So our most common state would be 0. A lot of times we don't show that. We would just write Kr. We don't actually have to show a 0 at all because it's neutral. Okay? So those are the most common states of ions, of elements that we know in the periodic table based on how close they are to a noble gas. Okay? So I wanted to share that with you. Thank you for listening. We appreciate it. And you have a great day.